Okay, so we left off last time. We were talking about electron configurations, how to write electron configurations, how to write orbital energy diagrams like this. Okay, how to fill the electrons, up, 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 and then down, down, down. Okay, that's how we would fill it. Now we're going to talk about trends, some trends that we find on the periodic table, essentially. How we can predict a few different things about the elements based on the periodic table and their position on the periodic table. So atomic size, we can predict from the periodic table. And so if we look at lithium, okay, it has a mass of 6.941, and fluorine has a mass of 18.998403. Which one would you say is bigger in size?
Bottom.
Which one?
Bottom.
Well, they're across from each other.
Like the one to the right of it.
Oh, this one, fluorine. Okay, so that makes sense, right? Fluorine would be bigger. It's heavier. It's got more electrons, etc. Right? Okay. So the thing about atomic size that you have to remember is it's counterintuitive. Lithium is bigger than fluorine. Fluorine is one of the smallest elements besides neon, helium, and hydrogen, which we're not really going to talk about too much because we already know that hydrogen and helium are super small. Okay, they're tiny. But when we get here to the second energy level, that's when we get kind of confused about the size because we're saying, oh, wait, lithium is smaller than fluorine. Size actually decreases as you go across a period from right to left. Okay? So the reason for that is if you consider lithium, here's the nucleus of lithium. Well, here we go. How many protons are in the nucleus of lithium? 3. 3 protons, right? How do I know that? Because it's number 3. Okay? Actually, I'm going to draw this over here a little more. Fluorine has how many protons? 9. Okay? There are 1, 2 energy levels around both of them. Correct? There's 2 electrons in the in the first energy level on both. And on lithium, there is 1 electron, 1 valence electron in the second energy level. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. Okay? Now, here in the nucleus are the positive charges. Okay? Whoops. So this first energy level creates a shielding effect. So here I have 2 electrons, and they are shielding this electron from the pole of these 3 protons. So these 3 protons, they have to reach out to this electron past these 2 electrons right here in that energy level. Okay? So they're trying to reach out here and grab this 1 electron. They have a very difficult time doing that. So because they cannot hold on to it all that well, that 1 electron pushes away from the nucleus. There's an attraction there, it's just not a super strong attraction. Okay? So it starts to pull away from the nucleus, which causes the atomic size to increase. Causes your atomic size to be bigger because the electron cloud has grown. That one electron is filling that space. And it's a big space because it's not being pulled tightly towards the nucleus. So we contrast that with fluorine here, which has 9 protons. Those 9 protons very easily push through those first 2. And they grab those outside electrons and they pull them. They pull them in tight. So the electron cloud does this. It contracts. And it's being held tight. Okay? In fact, lithium, does it want to gain electrons?
No.
No, not at all. It doesn't have the electronegativity to do that. It wants to what? Get rid of this one electron so that it can only have these 2 valence electrons instead of this one. Okay? So it wants to lose that one electron. So what about fluorine? What does it want to do? It wants to gain electrons. So it's holding onto its electrons tightly, and in fact, it would like to get another one. Okay? It has a strong enough positive character in its nucleus that it's happy to gain one more electron. Okay? That's part of it. Also, the valence shell is the other part of it, to have an octet. Okay? But it has the proton character to do that, whereas this guy doesn't. It's barely holding on to that electron. Okay? So, fluorine has a small atomic size. Okay? That's what you need to remember. Fluorine has a small atomic size. What's bigger, oxygen or fluorine?
Oxygen.
Oxygen is bigger than fluorine. Nitrogen is bigger than oxygen. Carbon is bigger than nitrogen. Okay? Lithium is bigger than beryllium.
Does this apply to every energy level?
Every energy level. Okay? As you move across, it's going to increase. Now, when you get into the D's here, it's not as consistent. Okay? So it's mostly of the representative elements. That's how we're going to look at it. The S and the P elements. The D and the S, they kind of have a more consistent size to them. So it's not as regular of a pattern. Okay? So, but we're not going to worry about those ones. Mostly we worry about the S and the P elements, the representative elements. Okay? So fluorine is small. As I go this way, that size increases. As I move down, what do you think happens?
Size increases?
Yeah, because I'm adding entire energy levels. Okay, here I have 2, 3, 4, 5, 6, 7. Okay, so it's getting bigger each time because I'm adding an energy level to it. And it's increasing its size. Okay, so what would you predict to be the largest element found on the periodic table?
Bottom right?
But yes. Francium?
Yeah.
Okay? Yes, that's the one. 87. Okay? That's the one that we would predict to be the largest. It has 7 energy levels surrounding it. Okay? So its protons have to reach through all of those energy levels and grab that one single electron, and that one single electron is barely hanging on. In fact, it requires so little energy to remove that electron that francium is one of the most reactive elements there is, because just the slightest amount of energy and that thing becomes explosive. Okay? So it's barely holding on to that one electron. All right? Okay. So when we're talking about atomic size, the size of an element increases moving down from top to bottom. it decreases moving from left to right. So it's decreasing. Lithium's big, fluorine's small. Now, we're not really talking about these guys because it would still follow the trend. The neon's smaller than fluorine, okay? But these aren't really the representative elements because they're inert. They're non-reactive. So when we talk about these trends, we often don't talk about them because it's not that important to understand their characteristics as it is to understand the characteristics of these guys. So that's why we often start with fluorine. And we talk about, okay, fluorine is small. As I move away, it increases in size. Okay? As I move away from fluorine in any direction, the size is increasing. Okay? That's the first trend. So here you can kind of see that. Like I said, the D's don't really follow very well that pattern. But we'll focus more on these representative elements. Fluorine is small. As you're moving away, size is increasing. They're not showing francium and radium, but here we get to cesium. You can see that the size is very large. Okay. So that's the trend that's being considered here. Okay. Okay. Now, what happens if I lose an electron? Now what's going to happen to the size of my atom? It's going to get smaller. Why?
Now it's going to have an extra proton pulling harder.
Yeah. Now it has more. The protons are outnumbering the electrons. What determines the atomic size? How strongly your electrons are attracted to your nucleus. So if I outnumber my electrons, they will be pulled in tight, right? So if lithium loses its one valence electron, it now has 3 protons and only 2 electrons. So it can pull them in tight, right? And also, what else happened when I lost that one valence electron? Okay, let's go back here. Look what happens when I lose that valence electron. You lose an entire energy level, right? It's gone. So not only am I pulling those in tighter, but they were already close. And now I'm going to pull them in even closer. Okay? Because I have 3 to 2. And it's going to get pulled in tight. What do you think? What's going to happen to the atomic size of fluorine when it becomes an ion? It's going to get bigger. Because why?
It's now more negatively charged on the outside.
There's more negative charges. There's more electrons than there are protons. And so they pull away from the nucleus. And the electron cloud is going to increase in size, right? So when I'm considering the size of my ion, what I need to do is I need to consider the number of protons and the number of electrons. Which is bigger? Lithium plus, let's see what they have. Okay, which is bigger? Lithium plus or Be2 plus?
What's bigger?
Lithium plus is bigger. Why?
Because they have more electrons.
No, they have the exact same number of electrons.
Because it lost one less.
Well, Be has one more proton.
Exactly. Same number of let's consider how many protons we have for lithium. 3, right? How many electrons do we have for lithium? 2. Beryllium has how many protons? 4. How many electrons? 2. When it's Be2 plus, right? Who's going to pull the electrons tighter? Be2 plus. It has 4 protons, 2 electrons. It's going to pull them tighter and closer than lithium plus. So when I'm working with ions and I'm trying to understand which one is bigger, I need to look at the number of protons versus the number of electrons. Okay? And it will tell me this one is bigger. Okay? So here you can see that. Well, let's go back. Let me ask you another question before we get there. Okay. Which one is bigger?
Yeah.
Okay. Why?
Its electrons are outnumbering its protons.
More than the others.
Yeah.
Okay, so how many protons do we have on nitrogen? 7. Oxygen? 8. Fluorine? 9. How many electrons do we have on each of these? 10. They each have the same number of electrons. They're isoelectric. Okay? They all have the exact same electron configuration. N3 minus, O2 minus, F minus. They all have this electron configuration. They all have 10 electrons. But they have different number of protons, 7, 8, 9. So 7 electrons, or 7 protons, 10 electrons, that's going to be the biggest one. Right? Because the electrons are not as strongly attracted to the nucleus as they are with O2 minus or F minus. Okay? So this one, this is what you should do. Label it, list it out like this. So you can see how many electrons and protons there are, and that will tell you which one's bigger. Okay? If it's an ion. Okay? So this is how we'll consider it when it's an ion. If it's an ion, that's what we look at. Okay? So we can see that happening here. So here, fluorine started at 71 picometers, and when it became F minus, it jumped up to 133 picometers. Oxygen started at 74 picometers, and when it became an O2 minus ion, it now went to 140 picometers, which is bigger than F minus, which is 133 picometers. Okay? But now look at these guys. Lithium was at 74 was at 152. Okay? Here, fluorine started at 71. Lithium was at 152. So this was significantly larger than fluorine. But when it became an ion, it lost its electron. It dropped down to 74 picometers. Okay? But look at beryllium. Beryllium went all the way from 111 to 35 picometers because it has 4 protons and only 2 electrons. So those electrons got pulled in super duper tight. Super duper tight. Okay? So that's probably the smallest atom you're going to get. Right there. Beryllium, 4 protons, those 2 electrons. There's no other situation like that. Helium has 2 protons and 2 electrons. So it's going to be not quite like beryllium that has 4 and 2. Okay? So Be2 plus is going to be smaller than He and H. Okay? All right, but that's how we would predict that. Okay? We can see that it works how we think it should. Okay? So 184, which is bigger than 181. This lost 1, this lost or gained 1, this gained 2. So the number of protons are outnumbered more greatly here than they are here. Okay? So the more electrons you gain, the larger you're going to become because you're outnumbering your protons. Okay, ionization energy. And this is all related. How strongly your electrons are attracted to your nucleus determines these other things. like the ionization energy. Ionization energy is the energy required to remove an electron from your atom. Okay? So if I'm going to remove an electron, how much energy do I have to absorb to do that? That's what the ionization energy is. Okay? If I absorb enough energy, I will remove an electron. It'll pop off. Okay? So you can see that here, sodium goes from Na to Na plus, and it lost an electron due to the ionization energy. Okay? The lower the ionization energy, the easier an element loses the electron. Which element do you think has the lowest ionization energy? That loses the electron more readily than any other element on the periodic table.
Hydrogen.
Francium. Not hydrogen. Look at francium. How many energy levels does it have? 1, 2, 3, 4, 5, 6. The thing's ginormous, right? It has one single electron way out there, and it has these protons right in the nucleus trying to reach all the way out and grab that one electron. It does not require very much energy at all to knock that electron off of there and cause francium to become reactive. Okay? Very, very, very little energy. Okay? Hydrogen has an electron very close to its one proton in the nucleus. So no, it's not hydrogen. Okay? So the trend for ionization energy is that fluorine, well, let's see, what do you guys think? Is fluorine going to have a high ionization energy or a low ionization energy? Francium has a very low ionization energy. Very little energy is required. What do you think the energy is for fluorine would be to remove an electron? High, right? Does it want to lose electrons? No. No. It has its electrons pulled nice and tight into its close to its nucleus, right? It does not want to lose them. It wants to gain electrons. So it has a high ionization energy. What do you think happens to the ionization energy as I move this way and the atom gets bigger?
It's lower.
It gets lower. So lithium has a lower ionization energy than fluorine. What do you think happens to the ionization energy as I go this way?
Decreases.
Decreases also. It gets smaller. Why? Because I'm adding energy levels. And I'm having a harder and harder time holding on to my electrons. Okay? So this is how this non-metal metal kind of situation occurs. Because these guys, they hold on to their electrons tightly. They have high ionization energy. These non-metals have high ionization energies. And as you move here, all the way over here, they have low ionization energies. They will lose those electrons with just a little amount of energy. So the ionization energy decreases as I move away from fluorine. That's the trend. And it's all related. Do you see how it's all related? The ionization energy is related to the atomic size because of how strongly the electrons are attracted to the nucleus. So they all follow the exact same trend. You start with fluorine. As you move away from it, your atomic size will increase. You start with fluorine. As you move away from fluorine, your ionization energy will decrease. Okay? So the trends are all starting in the same place, and they're either increasing or decreasing based on where we're starting with fluorine. Fluorine has a small atomic size. Fluorine has a high ionization energy. Okay? Okay, so we can kind of see that trend right here. Okay? Happening. Helium, neon, argon, krypton. Okay? They're just moving down here, and you can see that that ionization energy is decreasing there with that. And also neon, fluorine, nitrogen, oxygen, carbon, it's decreasing as you're moving down across a period as well. Okay. Okay, electron affinity. Electron affinity is essentially the opposite of ionization energy. So ionization energy, you lose electrons. Electron affinity, you gain electrons. Basically, what is your attraction for electrons? Do you have a strong attraction for electrons, or do you have a weak attraction for electrons? Now, the actual definition of electron affinity is the energy released when you bind an electron. How much energy is released when you bind an electron? The more energy released when you bind an electron, the stronger your affinity for electrons. Okay? Energy changes when a single electron is added to an isolated atom. That's how we define it. That's the electron affinity. So what do you predict fluorine to have? A high electron affinity or a low electron affinity? High. Fluorine has a strong attraction for electrons, which means when an electron binds to fluorine, it releases a lot of energy. It has a high electron affinity. What do you think happens as we move away from fluorine on the periodic table? What happens to the electron affinity? Decreases. Metals have a higher, non-metals have a higher electron affinity than metals because metals want to lose electrons. They don't want to gain electrons. Non-metals want to gain electrons. Okay? So that's how this periodic table situation is being created here. Non-metals, high electron affinities, high ionization energies, high electronegativities, which we'll get into also. Metals, low electron affinities, low ionization energies. Okay? Low electronegativities. Okay, and this is also showing that, once again, that kind of that trend that's happening there. Okay, well, that's weird. So that's the end of chapter 6. Okay? So be sure to get your chapter 6 homework done. Next class, I'll pass out the chapter 7-8 homework. Basically, it's going to be, this is a compound, draw a structure, tell me the geometry of it, tell me the hybridization of the bonds, tell me the formal charges, and you're going to have like 15 or 20 of those, okay, to tell me all those, how many sigma bonds are there, how many pi bonds are there, etc. Okay, so that's kind of what that homework will be like. You're going to draw it, you're going to fill out all the parts of it, okay, and then you'll have, so I'll give you like 15 or 20, and then I will randomly choose a few of those to be on the next test. And okay, so you'll have to, be prepared to know how to do that. All right, so let's talk about bonding here. So here we see the Lewis structures of a few of these elements, the representative elements. Okay, 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. We can predict that from the periodic table, right? So we know how many valence electrons each of these guys have. And we say that this is a Lewis dot structure, okay? Now, the Lewis dot structure is valuable a lot of times when you're showing electrons being added or removed from an element. So like for sodium, Na has 1 valence electron, and it goes to Na plus, and it lost that electron, plus E minus. Okay, so this would be the Lewis dot structures for sodium and sodium plus. Okay, essentially. Okay, electronegativity. So electronegativity is really why things either become ionic compounds or covalent compounds. So when we're talking about ions, those are things that gain and lose electrons. But fluorine and oxygen don't always gain electrons just for the heck of it. It has to react with something that will give away its electron before it can gain it. Okay? That's that oxidation reduction. You lose your electron, I'm going to gain it. But you have to give it away. And why do you give it away? Because I want it. But so if magnesium and chlorine are in each other's presence, magnesium will give his electrons to chlorine. But if chlorine and oxygen are together, are reacting together, it's not the same situation. Why? Because chlorine and oxygen, one of them doesn't want to gain and one of them doesn't want to lose. It's not the same situation. Those guys both want to do what? They both want to gain electrons, right? Oxygen doesn't want to give its electrons away to chlorine. Why? Because it has a high ionization energy. So does chlorine. Chlorine and oxygen have high ionization energies. So you put them together, they're not going to be like, okay, well, I'll give you mine and you can have them. Okay? Nope, that's not how they're going to act. So what are they going to do instead? They're going to share electrons, right? They're going to share electrons. So this is how we're creating these differences between something that is ionic and something that is covalent. Covalent is the sharing of electrons. Ionic compounds are where I give my electron to you, you gain it. Okay? And that's how the metals and the nonmetals form these ionic compounds, and the nonmetals form covalent compounds because they share electrons. These guys will pass electrons between each other. Okay?
Isn't it like ratios for the ionic compound as well?
Isn't it what?
Like ratios, pretty much.
Ratios. Oh gosh, I thought you said racist. No. Okay, ratios. Yes.
Right.
For the ionic compounds,
Yeah.
they form ratios, absolutely, because magnesium has 2 electrons and chlorine only has 1 that it needs. So I need 2 chlorines to balance out the 2 electrons that are being passed from one single magnesium.
So they're just pretty much sticking to each other.
They're what?
They're just sticking to each other, not like.
They are. It's like magnets because it's absolute opposite charges. I have 2 positive charges on a magnesium, and each chlorine has a single negative charge. So I have to have 2 of those chlorines to balance out that positive charges on the magnesium. Okay, so we get MgCl2 in those ratios. They have to be in the correct ratios based on their charges. That's what we learned about in naming, right? Mg2 plus Cl minus. Okay, so that means I need 2. Oops. The keyboard was writing. Okay. So let's see if we can. So we have Mg2 plus Cl minus. So that means I need 2 Cl minuses for 1 Mg2 plus. Okay, based on the charges here. This need 1, and so I get MgCl2. Okay, so here you can see these electronegativities. These are the electronegativities of the elements. They follow the same trends as the ones that we just talked about. Fluorine has a high electronegativity. As I move this way, what's happening to my electronegativity? It's decreasing. From fluorine to lithium, right? It's decreasing. So lithium has a low electronegativity. What happens to the electronegativity as I move down? It's decreasing also. Do you see that? My electronegativity is decreasing. It's decreasing. So they're following that same trend that we just talked about. You start with fluorine. As you move away from fluorine, the electronegativity will decrease. Now, the benefit of having this chart for electronegativity purposes is because we can actually calculate the electronegativity differences between 2 elements. And that electronegativity difference will determine whether you will be an ionic compound or a covalent compound. Okay? So here you can see that if the difference of electronegativity is between 0 and 0.4, you will be covalent. You will be a covalent compound. Okay? If it's between, so when I say covalent, I mean purely covalent, like nonpolar, purely covalent. But if it's between 0.4 to 1.9, now I am going into I'm creating a polar covalent bond. That doesn't mean my molecule's polar. We'll talk about that later. But I am creating a bond that is polar covalent. Not ionic, but there's an unequal sharing of electrons. Covalent molecules share electrons, and if they share them equally, it's covalent, purely covalent. But if you share them unequally, meaning oxygen is more electronegative than hydrogen, and so when you bind hydrogen to oxygen, that electronegativity difference creates a situation where oxygen wants the electrons more often than he lets hydrogen have them. And so you create a sharing, but it's an unequal sharing. Oxygen gets the electron more often. So it creates a polar bond, where oxygen becomes partly negative and hydrogen becomes partly positive. So water is a polar molecule, H2O, because there's an unequal sharing of the electrons between the hydrogens and the electronegative oxygen, because oxygen is highly electronegative. Okay? So between 0.4 to 1.9, polar covalent. And 1.9 is teetering. But then when you pass that 1.9 point, if you get a electronegativity difference greater than 1.9, you will then become ionic, because that electronegativity difference will cause one of those elements to lose the electrons and the other one to gain them. Okay? So that's how we look at this. So that's why if I look at a compound between oxygen and chlorine, okay, oxygen has an electronegativity difference of 3.5. Chlorine has an electronegativity difference of 3. So what, not difference, but an electronegativity of 3. What is the difference between them? 3.5 minus 3, 0.5. So it's a 0.5 difference. So where does it fall? Okay? Right after the 0.4, right? So it's polar covalent. So it's slightly polar covalent. Just a little bit, but it is. Okay? Look at oxygen and hydrogen. 3.5 and 2.1. Okay? So we have 3.5 minus 2.1. Okay? So we get an electronegativity difference of 1.4. So it is very polar covalent. Okay? It's into that polar covalent region. Look at HF. Okay? That's 1.9. Right? That's right there. It's almost ionic. It's barely even covalent. HF, hydrogen fluoride, or hydrofluoric acid. Okay? It's barely in that covalent region. It's teetering at becoming ionic, because fluorine has such a high electronegativity. Okay? Okay. Okay, here you go. HF 1.9, HCl 0.9. Okay? So HCl, that is definitely just polar covalent, but HF is getting really close to being ionic. Okay? Based on its electronegativity. Okay, so we would say HF bond is more polar than the HCl bond in that regard, because of the electronegativity differences between them. Okay, and this is a good little chart to show you where everything falls. Covalent, polar covalent, and then past this we become ionic. Okay, so we're going to classify these as ionic, polar, covalent, or polar covalent or covalent. Okay? We actually already looked at HCl. So HCl, if we go back here, oops, actually right here, it's already right here. Okay, HCl is 0.9. So what is it? Polar covalent. Okay. Fluorine has an electronegativity of 4. K has an electronegativity of 0.8. So what is this going to become?
Ionic.
This one is definitely ionic. Okay? Huge electronegativity difference between them. Okay? So definitely, this is much greater than 1.9. Okay? The carbon-carbon bond in H3CCH3. Purely 100% covalent. Because they both have the exact same electronegativity, right? I don't even have to look at it. Carbon has the same electronegativity as itself, bonded to one another. That's purely covalent. The electronegativity difference is 0. Right? So anytime you have a molecule that is bonded to itself, a diatomic molecule, for example, like O2 or H2 or F2, then those molecules are purely covalent. They have electronegativity differences of 0 because they're bonded to themselves. Okay. So we're going to talk a little bit about Lewis dot symbols and structures, okay, that he proposed back in 1902, okay, which are going to show your nucleus, okay, and the electrons, okay. So the dots represent the outer valence electrons, okay. So we don't really actually identify the inner core electrons in these. They're not really shown. You just understand that they're there. So we're only really looking at the valence electrons when we do this. Okay. So here you have nitrogen, and you can see it's drawn in all kinds of different. It's fine either way. What you're representing is 1, 2, 3, 4, 5 valence electrons on nitrogen. But people always ask, well, do I have to have it in any particular spot? Not really. You just need to show that you have those 5 valence electrons on a nitrogen. Those are the valence electrons. Okay? So we can see those for these different elements. Moving down the periodic table, you would obviously have the same Lewis dot structure. Okay? So oxygen and sulfur both have the same Lewis dot structures because they have the same number of valence electrons. Boron and aluminum also have the same Lewis dot structure because they have the same number of valence electrons. Okay, now let's talk about Lewis structures. Okay, this is a little different than the dot structure. Okay, so here in the Lewis structures, we're actually going to use lines to represent bonds. So the dots on a Lewis structure represent electrons that are not bonded. Okay, unless you're showing the Lewis dot structure itself. So, for example, let me draw water. Okay, we know water has 2 bonds, right? So we would represent those bonds with lines. The non-bonding electrons are represented by dots. Okay, now that's the Lewis structure. The Lewis dot structure would be you have 2 dots for a bond. Okay? And there's 8 electrons around the oxygen to satisfy its octet. Right? So before it bonded to those hydrogens, oxygen only had 6 electrons. It had these two that were paired, and then I had two that were not paired. And then hydrogen had one unpaired electron for each of the hydrogens. So when they come together like that. And they pair those electrons there. And they satisfy, oxygen satisfies its octet by pairing with the two hydrogens. And hydrogen satisfies its valence shell because it can only hold two electrons in its valence shell. So they're both happy. Okay? Or, for example, if you had, let's go back here, two oxygens. These guys have 6, and this guy has 6. Could they satisfy each other's octets if they came together? Yeah, right? Okay? Actually, a better way to draw it would be more like this. Okay? So, what do you think we call this type of bond? A double bond. We call it a double bond. So, oxygen can satisfy that octet with itself by creating a double bond right there between each of the oxygens. Okay? Whereas here I have single bonds. These are single bonds. Each line of a bond represents 2 electrons. Okay? So this is how I would draw this in the Lewis structure. Okay? Here's those 4 electrons. They're represented by bonds. It's a double bond. Oxygen is double bonded to oxygen. Okay? All right. So there's certain rules that we want to follow to be able to draw these structures. Okay? The first one is count the total valence electrons from each atom in the molecule. If there is a negative charge, you're going to add an extra electron to that entire molecule. Okay? And if there's a positive charge, you're going to subtract an electron from the entire molecule. Then you're going to draw a skeletal structure, and you're going to put the least electronegative element in the center. So if I was bonding phosphorus and chlorine, which one would go in the middle? Phosphorus is less electronegative than chlorine, so phosphorus goes in the middle. That's right. So the least electronegative one goes in the middle, surrounded by the more electronegative one. Now this is the thing about these guys, fluorine, chlorine, bromine, iodine. For very basic structures, they can never go in the middle. Why? For basic structures, these could never go in the middle. Why? Think about their valence shells. They only need one more, which means they can only make what? A single bond, right? Can you be in the middle if you can only make a single bond? No. You will always be on the outside, right? If I make one single bond, I could never have 2 things attached to me. So these guys always have one thing attached to them. What about hydrogen?
Same.
Exactly the same. It can never be in the middle. It only has one electron that it can share. It can only make one single bond. Okay? So H2O. Well, we know which one goes in the middle, oxygen, because the hydrogens cannot be in the middle. They could never be in the middle. They're always on the outside. Okay? And we would basically consider that same thing here with these guys. They're always on the outside. The halogens, they're always on the outside. Except when they're on the inside, okay? But that's a whole different situation that we'll talk about when we talk about expanded octet. But for these general guidelines that we're following, those guys are on the outside. Okay? So we're going to draw this skeletal structure. We're going to put the least electronegative atom in the center. H and F always at terminal positions. Okay, that's kind of what we just were saying. Carbons can form carbon-carbon covalent bonds. So carbons could always bond to one another and then have attachments to those carbons. Okay. Connect central atoms to surrounding atoms. So, for example, if I was starting my water molecule over, okay, I would say oxygen is bonded to hydrogen, so we're going to attach them to the central element, okay, the hydrogens. Complete octets around every connected atom. How would I complete the octet on this oxygen? It's missing 4 electrons, right? Electrons pair. So I have to put them in pairs. Now that oxygen right there in the middle has how many electrons on it? It does. It has 8, right? 2, 4, 6, 8. Hydrogen has how many electrons on it? 2. Should I finish the octet on? Should I put 8 electrons around hydrogen? It's a big mistake people make. Do not put 8 electrons on hydrogen. Hydrogen cannot have 8 electrons around it. Why? Has a single energy level with 1 s. That's it. An s can only hold how many electrons? 2. So it cannot have 8 electrons. You have to have an s and a p to have an octet. Hydrogen and helium do not have s and p's. They only have an s. Therefore, they only need 2 electrons to satisfy their valence shell. Okay? So here, in this way, oxygen has 8, hydrogen has 2. That's satisfied. Everything's ready. Okay? Let's look at a different one. Let's try... okay, sulfur goes in the middle, surrounded by 2 oxygens. Everything needs to satisfy its octet. So what am I going to do? Okay, in pairs, I'm going to put 3 more pairs on this oxygen to have 8. Okay, so now it has 8. What am I going to do to the sulfur? It only has, right now it only has 4 electrons on it. It needs 4 more, right? Now it has 8. Now it has 8. Now everything has an octet. That's the starting point. You have to start where you only have single bonds and everything has 8 electrons around it. That's how I start drawing these structures. Okay? Every time. Okay. So draw a line between 2 atoms. A single bond equals 2 electrons. Complete the octets, except for hydrogen, lithium, beryllium, and boron. Okay? So this is what they're saying about that. How many valence electrons does carbon have? 4. It can spread all of its valence electrons out, and it could make up to 4 bonds. If I make 4 bonds, how many valence electrons do I have around me? 8. So carbon can complete its octet. It has the ability to do that because it has enough electrons. How many valence electrons does boron have? 3. It can spread its 3 out. It can make up to 3 bonds. How many valence electrons is that? 6. Is that a complete octet? No. Boron cannot complete its octet. So one of the biggest mistakes that people make is when they're drawing boron structure is they put 8 electrons on boron. Boron cannot have 8 electrons. What about beryllium? How many could it have? It can make 2 bonds, which is how many valence electrons? 4. Okay? So, this is that point. Everything before carbon cannot have a complete octet. Everything after carbon can. Okay? But right there before it, you cannot have a complete octet. So you will not put 8 valence electrons around any of those. How many valence electrons am I going to have around boron in my structure? 6. How many valence electrons around beryllium? 4. Okay? That's what I need to remember about those guys. Right there. Carbon is where it starts. The octet starts there. Before that, you can't. Okay? So these are those exceptions. Lithium, you're not really going to see as a covalent compound. It's mostly going to ever only be ionic. Okay? So you don't have to worry about it so much. But beryllium, every once in a while, you will see it as a covalent compound. BeH2. The electronegativities between beryllium and hydrogen are not large enough to actually force it into an ionic situation. So it becomes covalent. Okay? All right. Move electrons to satisfy octet rules. Make double bonds if necessary to complete those octets. Okay? So we're going to practice this. All right? Let's do carbon dioxide. So, first step. So I'm just going to simplify all this. First thing you always do is find the valence electrons in your structure. How many valence electrons are in a carbon dioxide molecule? How many valence electrons are on carbon? 4 electrons. Oxygen has how many valence electrons?
6.
Times 2? 12. 4 plus 12? 16 electrons. There are 16 valence electrons in the structure of carbon dioxide. Okay, I started out, which element goes in the middle? Carbon, because it's the least electronegative. Carbon surrounded by 2 oxygens. I want to satisfy the octets of everything. That's my starting point. What do I do to this oxygen?
6.
I put 6 electrons around it. Same thing here. What do I do to the carbon in the middle? 4 more. Okay? 2, 4, 6, 8. Oxygen has 8. 2, 4, 6, 8. Carbon has 8. 2, 4, 6, 8. Oxygen has 8. Now, count how many electrons total I have in that structure.
18.
Okay? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay? I have 20 electrons in my structure. Does that match this? It has to match. It has to be the same. So whenever you have too many electrons, which will always be the situation, unless you're dealing with expanded octets, which we'll get into later, but for what we're doing here, you will always have either the exact right amount or you will have too many. If you have too many electrons, to reduce the number of electrons in your structure, instead of having electrons that are not paired, if you pair them, it will reduce the total number that your structure can have. So I make a bond. If I need to reduce electrons, I make a bond. That's the only way you can reduce the number of electrons. So I make this bond here. Now look at the oxygen. How many electrons are on the oxygen that I just bonded to?
Still has
Has 10. It needs to have 8. So that means I need to remove 2 of those free electrons. It can't have those now that I made the bond. It can't have those. Look at the carbon in the middle. How many does it have? 10. Can you have 10 electrons? How many electrons do I have in my structure now? $18. So every time you make a bond, you add 2 electrons and you remove 4. That reduces the total number by 2, 20 to 18. Am I there? What do I need to do? Make a second double bond. I have to remove electrons from both of the things I bonded to. I need to remove a pair of electrons from both of the things I bonded to. Because I have to maintain the rule of 8. Am I following the rule of 8 here? Yep. How about this one? Yes? How about this one? Yes. So I am following the rule of 8. You need to check for that. Does it follow the rule of 8? If it does, that's good. If it doesn't, you've done something wrong. Okay? How many electrons are in my structure? How many do I need? This is my structure. How do I know? It has the right number of electrons, and it's following the rule of 8. That's my check. Okay? So, if you get something that's not following the rule of 8, you need to start over. You need to do it again, because it's wrong. Unless it's the exception like boron here. Okay? You can't follow the rule of 8 on boron. Okay. Let's try this one. Carbonate. Carbon has 4. Oxygen has 6 times 3. 18 plus 4. 22. Is that the number of electrons in this structure? Plus 2 is 24 electrons. Okay? There are 24 electrons in my structure. 24 electrons in my structure. How do I start it? I put carbon in the middle, surrounded by 1, 2, 3 oxygens. Now what do I do?
6 on the oxygen.
Each oxygen needs 3 more pairs to have 6 more electrons.
And 2 on the carbon.
And we call these lone pairs. They're called lone pairs of electrons. Okay? So oxygen here has 3 lone pairs. Carbon has 1 lone pair. Okay? How many electrons are in this structure? $26. What do I do?
Make a double bond.
Make a bond. Does it? Okay. So this is the question I always get. Which one do I bond to? It doesn't matter. We'll talk about resonance later, but it doesn't matter because that double bond will be distributed through around all those oxygens. Okay. So it really doesn't matter. Make a bond. Now what do I do? Remove electrons from both to maintain the rule of 8. 2, 4, 6, 8. 2, 4, 6, 8 on the carbon. 2, 4, 6, 8 on that oxygen. 2, 4, 6, 8 there. Everything has 8. How many electrons are in the structure? As I've drawn it, how many are there? I had 26. I have 24. You reduce it by 2 every time you make a bond and remove 4 electrons added 2. Okay? So I'm at 24 electrons. This is my structure. More correctly, I would say 2 minus. Okay? This is my structure. That's it. If you follow that procedure, you can draw any of these structures that I throw at you. Okay? So that's all there is to it for drawing these structures. It's not too hard. As long as you figure out how many valence electrons you need, start everything out with 8, and then remove electrons as you need to get to the correct number of valence electrons. Okay? Okay, try that one. Okay, is this what you guys were finding? So I didn't have to manipulate it at all, right? 20 electrons, I start out with 20. So one thing that hopefully you might become familiar with, okay, is that if it's something bonded to 2 things, your structure will always start out with how many electrons? 20. If I make 2 bonds, I'm going to start out with 20. If I make 3 bonds, I'm going to start out with 26. Okay? If I have 4 bonds, (32) 32 electrons. Okay? So, NO3 minus nitrogen equals 5. O3 equals 18. 23 plus 1, 24 electrons. Okay? Without even drawing the structure, just knowing this, if I have 3, this is where my starting point, right? Because it's NO3, I have nitrogen, 3 oxygens. I'm going to start out with 26 electrons. What do I already know is I need?
Double bond.
I need 1 double bond, and I'll have 24. I didn't even have to draw it. Okay? And I can perceive that. I can see, oh, I know I'm supposed to start out with 26. I have 24 electrons. That means I'm going to have a double bond in my structure. Done. Okay? Okay, we'll practice this some more next time, guys. We'll see you.